started to discuss the motion of a fluid, and we said that just a few general words about it, like that there are two descriptions. The Lagrange description, in which you do the following: you take a you imagine to have a fluid particle, so to say, and you observe how it moves. So if originally the part at t equals 0, the particle was at the position x, the trajectory will be, generally speaking, given by the formula y of x and t, and that will be the trajectory of this fluid particle. You can imagine that you put a drop of dye on this, and then you observe how it moves in the fluid. And that's the Lagrangian coordinate. Now, we also said that, so y is a function of x and t, and of course, by definition, the initial value of this is just x. Now, another description is to look at the fixed given. So this Lagrange description is comoving description. You move with the flow. There's a Euler description, which we discussed, in which we simply say we have velocity v alpha. Alpha is 1, 2, 3, or depending on dimension, which depends on x and t. So you put a monitor at some fixed point, and then you read what it shows. The relation, and we briefly discussed the relation between the two. It is actually quite simple, although not completely trivial. We said that y alpha dot should be equal to the velocity if our fluid particle is at the position y. Its time derivative should be equal to the velocity of y and t. Notice that this is a non-trivial differential equation. It's not. You see, if we put x here, that would be kind of trivial. You integrate it and that's it. But here we have to do some non-trivial work when we want to pass from, say, Euler to Lagrange. It's not trivial, and as you know from the general differential equations, from the theory of general differential equations, to specify a solution, you need to specify the initial value of y. Then this initial value is just x, and in this way you get y of x and t, and x plays the role of the initial position. I can give you a almost trivial example. Suppose that, which we actually will need later. But, suppose we have v alpha equals to cy alpha. Then what do you think will be the Lagrange trajectory y alpha of x and t? Yeah, actually y alpha of x and t, as you see, is just x alpha e to the power of ct. So it is just expansion. And we will return to this example a little later, maybe in this or in the next lecture, discussing, believe it or not, exponential expansion of the universe. But at the moment it's just a mathematical example so that you get the feeling what you have to do with this relation. Now we actually have to derive the equations of motion for the fluid. So far this is just kinematics. It's not there is no dynamical elements here. Again, we derive the equation in a very simple way. We simply say that we have a fluid particle. We visualize the fluid particle, and it moves in the potential created by all other fluid particles. We don't know what it is, but we can write down the following relation. If we have, let's suppose, I have to add one more thing. Let's derive the equation of motion first in the case when the fluid is incompressible. Incompressible, you will see a little later what does it mean. It means that basically the density is constant everywhere. So we have this constant density, which is the mass of the fluid particle, multiplied by acceleration, and it should be, according to Newton, some potential, which for the reasons you will see I will denote by P. And the gradient acceleration is equal to the gradient of the potential, and P is some function. P, generally speaking, can depend on y and t. The physical meaning is the potential acting on this fluid particle. As you will see in a few minutes, it's just the pressure which you have in the fluid, but so far it's not obvious. So far it's just the unknown potential. So we have a problem here because we have an unknown function, and we have more unknowns than the equations. We have 3 equations, but 4 unknown functions. So we need one more relation to be added to this. The relation simply follows from incompressibility. Incompressibility means that if you have a volume in this space and the volume moves, it changes its shape, but since the density is constant, it actually doesn't change. The volume is the same, so that follows from mass conservation. The mass here is just the density multiplied by the volume, and the density doesn't change. So we have to conclude that the volume doesn't change, and that basically you can take it as a definition of incompressibility. Now, we several times already encountered with the change of the volume. It's a general mathematical question. Namely, you have some map y alpha of x, and you want to know how the volume changes, say, under infinitesimal transformation. If I look at it's just pure math, it's not physics yet. If we take as an example one dimension, we have an interval in the x, and it is mapped by the function y of x into something else, delta y. And of course, you know that delta y, the size of this interval, the length, which is one-dimensional analog of the volume, is just y prime of x multiplied by delta x. And so we know that when you change variables in the integral, when you go from variables x to the variable y, you just have to multiply by the derivative of y. Generalization, we discussed generalization of this rule. And we now want to see, we have y, say x1 and x2, x2 and x1. We have some domain, and we have a mapping given by the formulas. I am now doing it in 2 dimensions, and after that it will be. And mathematical question, the mathematical question is, if you know this delta dx1, dx2, how to find the new volume? And the answer is very simple. Do you remember the answer? We actually discussed it at some point.
The determinant of the Jacobian.
The what?
The determinant of the Jacobian.
Exactly, yes. What replaces simple derivative is the determinant of the matrix dy alpha dx beta. So the volume, the new volume, is equal to this multiplied by so now we know what we should add to the equation. And what we should add to the equation to get a complete set of equations is simply the condition. So maybe you tell me what should we, if we are talking about motion of incompressible fluid, which preserves this thing, what should be, and we need one more equation because we have 4 unknown functions instead of 3. So what kind of equation we should add to this?
The divergence of the velocity is 0.
But that's in principle correct, and we will derive it. It's still, but we don't have the notion of which velocity. You see, so we have variables. Our variables are just these ones. We want description of. We want the description of Lagrangian description at this point. And so you have to formulate it in Lagrangian terms. And the answer is very simple.
The determinant is 1.
Yes, that's just it. And now these 2 equations are complete. Complete in the sense of, well, as you know, it's the best way to familiarize you with the new equations is just to look at some simple solutions, and then you will see a range of in which equations have applicability and limitations, etc. That we will do in a few minutes. But at the moment, I just want you to, I want to stress that this is a complete set. And you mentioned the fact that divergence of velocity is 0, which is correct. We will see it in a moment from this equation. Now let's, as I also told you before, that both descriptions are needed. Actually, in some problems it's better to work in Lagrangian variables, in some problems in Euler variables. And you see that in Lagrange variables, it's pretty difficult, pretty complicated equations. It's highly nonlinear. It will be also nonlinear in the Euler variables, which we derive in a moment, but it will be less, well, in a sense, it will be less complicated. But you see, this nonlinearity is extremely crucial. It provides us with, it's only because of that the whole richness of different phenomena can be described by this equation. And this nonlinearity will be at the center of what we are going to discuss. But it is also, it gives the richness to the equations, but it also gives a complexity. All right. Let's derive still, before we go to concrete physics, we need to derive, we need several things to be done. First, we will derive Euler equations, then for incompressible case, then we have to repeat this derivation for compressible case, which is also needed. All right, so let's now, well, the derivation of the Euler equation is now completely straightforward. We have this relation. Let's differentiate it with respect to time. As we differentiate it with respect to time, we have, there is a slightly non-trivial point, because notice that here time dependence enters here and here. Y depends on time. So to be, I probably should have written it down more explicitly like that. Okay, so when you differentiate, you have two terms. You have the term V alpha dot, plus we have to differentiate this guy. We will get Y beta dot d beta d alpha. And this is equal to d beta, I remind you, my notations, well, they are common notations. And so the first equation is, so this is Lagrange, and now Euler. And the first equation is simply rho 0, the density V alpha, which can be set to 1 in the incompressible case. So the meaning, actually it's quite easy to understand the meaning of this equation. This nonlinear term, it has its origin in this time dependence, and what it means is something quite simple. You have, if you look at the fluid particle and you want to measure the acceleration of the fluid particle, you have to compare the moments t and t plus delta t. So this is interpretation. Here the velocity was v alpha of x t. Here, at the moment t plus delta t, so that was the original velocity. The new velocity after the moment of delta t will be v alpha of x plus delta x, because the particle moves, t plus delta t. And delta x is just v beta, delta x beta is v beta delta t. And now you expand and you get this second nonlinear term. So it's just the fact that takes care of the fact that V alpha is associated not with the fluid particle, but with a given position in space, while we want acceleration of the fluid particle. So because of that, we have to look at the velocity in the new position occupied by the fluid particle. Well, whatever. If it's confusing this way, it's completely trivial to derive formally this way. But that's the origin of nonlinearity of these equations. And now there is one more point to be made, and we have to rewrite this equation in terms of the velocities. And once again, let's differentiate it by time. And I suggest that you do it yourself at home, looking at our lectures on Hamiltonian system, to which we have to comment also, that this equation is equivalent to the equation that divergence of the velocity is 0. So the second equation here, if you have problems with the derivation is based on the formula for the determinant. Determinant, if you want to differentiate the determinant with respect to time, it's done very simply. You write down first the determinant as e to the logarithm of the determinant of m. I'm just sketching this. This is trace of the logarithm of m. And when you differentiate, you get d dt of log determinant is equal now, when you differentiate the logarithm, you get m minus 1. Get trace m minus 1 m dot. And this formula, by the way, is this transition obvious? From here, how you derive this transition, the fact that logarithm of the determinant is equal to the trace of the logarithm. I suggest that you remember how the determinant is expressed in terms of the eigenvalues of the matrix. So imagine that you diagonalize the matrix, then what you get?
So just the product of the eigenvalues?
Yeah, it's logarithm of the product of eigenvalues, and this is sum of the logarithms. And sum of the logarithms is the same as the product of a logarithm of the product. So it's very often used and convenient formula. Using this formula, I don't have time for that now. We are a little bit slow, going a little bit slow. But we already believed it. You already encountered with it when we discussed Hamiltonian dynamics. At what point we looked at this thing? Which part of in mechanics is relevant for this discussion? Yes.
Is that Liouville's thing?
Yes, exactly. When we discussed the Liouville theorem, we just derived that I remind you, it's summation over alpha here. We just derived that this is the condition. Now, one general point which is worth making is, let's compare. So in this equation and in this equation, we have the motion of which preserves the volume. And so we have a Hamiltonian system. So what's the difference? Can you think of that's a simple but subtle question. What is the ideological, so to say, difference between the Hamilton equation and the fluid and the Lagrange equation as far as incompressibility is concerned. Well, remember, so maybe I should put the question more clearly. If you, let's compare it. Let's compare it with the Hamilton equation. In the Hamilton case, we have the symplectic form. That was the Hamilton equation. So what looks similar and what looks different? What's the analog of what's the natural analog of the Hamiltonian? Let's first start with it. What?
P.
Yes, which as we will see, is the pressure. So Hamiltonian is, this term is precisely the same. While this, here we have second derivative, here we have first derivative. Now, we could have also second derivative here if we interpret it as a motion in magnetic field and add the mass, it's just the limit. But the most important, what I wanted to stress and what I wanted you to realize is that here preservation of the volume is automatic. Namely, if here you have some y alpha of t, and we can introduce initial positions x, and the determinant, what Liouville theorem says is that if you take this thing and you take its time derivative, it's automatically zero. You don't have to, it's zero for any h. You see, you don't have to fine-tune h. Here, the pressure, when the fluid flows, the pressure is something concrete. You cannot, if you put arbitrary function here, the volume will not be conserved. It's a function which is which is chosen by this condition. While in the Hamiltonian system, any Hamiltonian preserves this volume. That's the difference. But at the same time, there are a lot of similarities, and I just touched some interesting subject. We can go deeper here. For instance, it's easy to write down the variational principle here and so on. Well, actually, maybe I should. Well, we don't need it right now. Okay, and the meaning of the meaning of this thing we will understand in a moment. Now, just one more step which I need before I start applications is compressible fluid. In compressible fluid, we have variables describing the system are the density. That's the Euler variable, the density, and velocity. And density, this time it is changing. It's function of x and t. The first equation simply goes unchanged because it has now the second equation is more tricky. What replaces, the question is what replaces this equation? It's not true anymore. And what replaces it is just that the mass, we show it's conservation of the mass. The mass of this guy should be equal to the mass of this guy. And the mass is actually, well, let me write down. It's easier to write down the answer, and then you will understand. That's is equal to rho 0 of x. Rho 0 here, the initial value of the density at t equals 0, or I can write it down as rho of x and 0. It's convenient to get rid of this, and that simply means that rho dy is equal to rho 0 dx if we are in one dimension. It simply means that as the system moves, the total mass of the given segment or of the given domain is not changing. And it's convenient to differentiate it with respect to time. This is 0. And finally, we get the second equation. Where is it? Where is the first? Oh, yeah. Okay, I shall write down again both equations. It's again very easy to transform it into the Euler form using this formula for the determinant. So once again, the formula for the determinant, d dt logarithm of the determinant of m is trace m minus 1 m dot. This formula is crucial, and as I said, I recommend you to play around with it to derive it and to give some examples and so on. It's very often used in physics. Anyway, using this formula, it's very easy to calculate time derivative, and now I'm writing the answer. I'm actually anxious to start doing some applications of this equation. The equations themselves are interesting, but you really get the feeling of their beauty and power when you start solving problems. This is just, it could have been derived directly, the continuity equation. Rho dot plus d alpha rho v alpha is equal to 0. The second equation, v alpha dot plus rho v alpha dot d beta d beta and this is the Euler equation, the general Euler equation. If the meaning of this this is called the continuity equation, and of course what it means is very simple. You take any volume in the fluid, so you integrate and you consider the quantity d dt of rho d3x taken inside this volume, the integral taken over this volume. So this is a total mass in the volume. Its time derivative is non-zero. Why? It's because just a few minutes before I was saying that the mass should be conserved and we used it and so on. And now I'm saying, let's calculate this thing, let's calculate its time derivative. It will certainly be non-zero. Why the mass doesn't disappear, but what can happen to it?
For a compressible fluid, you have some mass going in and out of the volume chosen.
I have what?
This is for a compressible fluid,
Yes,
mass coming in and out of the volume which you chosen.
that's right. The fluid simply can go away from this volume. And when you look at this thing, you use the Stokes theorem to say that it's and this is, well, maybe the minus. So you have it's simply conservation of mass in the sense that if you change mass inside this boundary, that means that it went through the boundary outside. This is the flux of the mass which goes outside. So the conservation law here, that's typical for continuous mechanics, that the conservation law is not simply that something is zero, that some time derivative is zero, but that for a finite volume you have this type of relation. And of course, the total mass, if you take infinite walls, velocity at the walls will be zero, and the total mass will be conserved. If v goes to infinity, then of course this is zero, and we have a conservation law. But it's very important to understand what happens when you have a finite volume. Okay, so now we still need one more equations, because now we have for compressible fluid. In compressible fluid, you see we have three components of velocity. We have density, and we have also pressure. And here you assume that the fluid is in thermodynamic equilibrium. Well, in other words, I shall tell you what we will be doing, and then I'll justify this. You assume that the pressure in the system satisfies some equation of state, some thermodynamic equation of state. For this, it's not an obvious assumption, because the fluid moves, and as it moves, everything ρ changes and p changes, while in thermodynamics you assume that everything is in equilibrium, nothing moves. You have just some average density, average pressure, and so on. So what do you think would be a criterion which allow you to use the naive equations of motion, the static, so say, equation of motion? For instance, if we're talking ideal gas, then P is proportional to ρ. If we are a gas at given temperature, if we have adiabatic situation, you isolate the system, then P of ρ is ρ to some power, and so on. But it's always a concrete function. And there is a physical assumption which allows you to use this function in the equation. Well, you see, when you perturb the gas, it starts relaxing towards equilibrium, generally speaking. And there is some characteristic time after which it reaches the equilibrium. Now we need that characteristic times in our problem defined by velocity and the size. So we have the size of the fluid, we have velocity of the fluid, we have characteristic time, the size divided by the velocity. This time must be much greater than the time of relaxation, than the relaxation time. So there is this serious constraint, but in practical application, well, sometimes it is relevant when the relaxation time, first of all, in classical hydrodynamics, it's never relevant because velocities are not that big, and the sizes, the length of free flight is always much smaller than the size of the system, and so on. There are modern examples when application of equation of state is problematic, and some of them are of great practical interest. Some unusual fluids. Turns out one of the unusual fluids is our blood. It's not really trivial to write hydrodynamics for the blood flow, but we will not be doing this. We are not bloodthirsty. All right. Anyway, if we return to innocent water, all these concerns can be forgotten, and water actually in most cases is just incompressible, in which case you don't need the equation of state. You determine the pressure from here. And by the way, you see how simple it is to express the pressure in terms of the velocity. If you take the divergence of this equation, you will get the relation, the Laplacian of P. This will be 0, so it will be rho 0, and here we will have d alpha v beta, d beta v alpha. And this is the Poisson equation, which is easy to solve and express P in terms of the velocity. And plug it back, you get but the price you pay for this simple step is some quite terrible nonlinear equation. All right, so these are the basic equations. Let's now find some simple and interesting solution. We begin with the case when we try to look at the linearized equation. And then we will see some nonlinear solutions as well. Well, we will assume that to familiarize us with the equation, we want to see to some approximation in which you can treat them as linear. What do you think is the general requirement under which you can neglect nonlinear terms? Again, it's kind of simple, and I'm asking some very qualitative question. When do you think it's reasonable to drop nonlinearities?
Much smaller than
Yeah. It's clear that velocity should be small, the deviation of the density should be small. We have to, and then probably it will make sense to treat them as linear equation. But of course, when you do such things, you make the guess. As you said, suppose they are small, find the solution, and then check. Then you go back to the exact equation and estimate the error. That's the strategy. Okay, so V alpha is small. The density we shall write down as rho 0 plus rho 1, and we will assume that rho 1 is also small. Then, so this is linear. We write down the continuity equation. Rho 0 is a constant. We will write down rho 1 dot plus V alpha is already small, we assume. So we have to write down rho 0, d alpha V alpha is 0. That's the first approximate equation. We do not want terms, we assume that rho 1 has smallness of the same type as V alpha, and when we don't want the product rho 1 by V alpha. Okay, the second equation should come from here. Once again, we have rho 0, V alpha dot. And here I shall write down minus, and it will be convenient for me to write it down as c square d alpha rho, where c square is by definition dp d rho. By the way, this quantity is compressibility. It tells you how much pressure you need to change density. All right, so we have this equation. And as we solve this equation, to solve this equation, it's convenient to take the divergence of this guy. And if we take the divergence of this guy, we get rho 0 d alpha v alpha dot is equal to minus c square Laplacian of rho. And it will be rho 1, of course. And here it's rho 0. And now you get the following relation. You get the equation rho 1 dot minus d square rho 1 minus c square this equation is, we already encountered with it. It describes what? We now can solve this equation very easily because it's linear. We will write down rho 1 as or simply, maybe we simply will be, I explained it already. We can simply look for the solution in the form of a of k e to the I k x. And as we discussed, we get the equation a double when you take the derivative acting on the exponential gives you k square. And you get so this is the equation for a harmonic oscillator. And so what this equation describes? What process? What kind of process? And we see that we have rho 1, the fluctuation of density, is proportional to some amplitude defined by the initial condition e to the I k x. It's of course you understand when you have complex things here, you understand that you take real part of it or imaginary part of it. Multiplied by Well, I shall write it down in a different way. So rho 1 is e to the ikx. I shall write it down as ak. Since it's the equation for harmonic oscillator, I will have two terms. That's the general solution of this equation, and omega k is ck. So what we're describing now? What physical process? What happens? I shall even write down in real. So you can also write it down as a cosine kx minus plus arbitrary constant. What?
It's a standing wave.
Why it is standing? Where is the maximum of the cosine? What happens to the maximum of the cosine? How is it standing or not? So cosine has an extremum, say, at zero value of the argument. So what it is in space-time in x and t? Just look at this formula and
Yeah, okay. So it's traveling.
it's traveling wave. For example, in one dimension, it's simply cosine k x minus ct, and it's traveling with speed c. And so it's just speed of what we're describing is sound. And c is the speed of sound. And we still have to we still have to evaluate the error which we made when we dropped all nonlinear terms, and we will do this. But at the moment, the solution which we found corresponds simply to the sound wave which goes with speed c. And we also see that the speed of sound is defined by compressibility, which is not surprising, but okay. The general wave, by the way, as I mentioned last time, the general wave you can get as a superposition of these ones. Here the wave corresponds to a particular value of the wave vector, but since the equations are linear, any superposition will be a solution. So you can multiply it by arbitrary function of k and sum over k. And I mentioned to you last time it's the fact that you have that the solution is superposition of these exponentials is related to translation invariance. It has a group theoretic origin. All right, but what is very important is to evaluate the error. So let me write down for the third time, I guess, of the Euler equation. So what will be the strategy if we want to evaluate the error? What would you suggest to do? we obtain the solutions, and we have exact equations. So suggest some simple test for the error which we are making. Actually, I will tell you that next time we'll find the solution, the exact solution for the sound, nonlinear sound, which is completely different. But at the moment we want just to evaluate our approximation. For example, what did we do when we can write it down as c squared d alpha rho. We dropped this term, for instance, when we derived this. We dropped all the nonlinear term. So when our approximation is good, the question is trivial, simple. Well, you know, since we dropped this term, it must be small in comparison with this one. Otherwise, it doesn't make sense. So that's, roughly speaking, the absolute value of this guy must be much smaller than the alpha dot. Okay, but now let us see what it means. If we have a sound now, what I'm going to do is actually more or less the standard procedure when you deal with the equation. You start evaluate orders of magnitudes of various terms. So what would be the order of magnitude? Suppose we have the velocity and it has certain order of magnitude. We derive the equation for density, but of course we can immediately, using any of these equations, we immediately write down the equation for the velocity as well. So what would be, if velocity is v, what is the order of magnitude of v dot? Suggest something for the sound wave written here. So we have a sound wave with a particular wave vector, and we want to evaluate v dot. And we know the amplitude of the wave. Suppose v is given. So how you evaluate v dot if v is given? Again, simple question.
Find the derivative.
The what?
Maybe if you find the derivative of v.
Yeah, but what is the order? It's time derivative, but what is the order of magnitude of the derivative of this guy? How fast it's typically time derivative measures how fast the quantity changes, right? So how fast this quantity changes in the sound wave? What?
CK times V.
Yes. It actually, the frequency, or as you said correctly, CK. All right. So we have the order of magnitude. What I'm trying to convey to you the method of order of magnitude estimates in this simple example. So as you said correctly, it's CK, the frequency, multiplied by the amplitude of the velocity. Okay, now we have to evaluate the left-hand side, which is, again, not difficult at all, although it is nonlinear. So maybe you will tell me, be bold, and tell me the order of magnitude of the left-hand side.
E squared K?
Yes. So kV square must be much smaller than CKV. And as you see, the condition of linear approximation is very simple. And you can also, I leave it for your homework, you can evaluate all other nonlinearities in the equation. We took care of one of them, but they're all simple and related to each other. And basically the answer will always be that velocity of the wave is much smaller than the speed of sound. By the way, it's kind of interesting that we have the wave in which our fluid particles, how it is possible that all fluid particles move with a velocity much smaller than the speed of sound, but the wave moves with the speed of sound.
So group velocity and whatever the other one is.
The what?
So the velocity of the group versus the velocity of a single point.
Well, yeah, you basically can visualize it. Well, one way of visualize it, it's the spread of rumors. People don't have to move very much to spread rumor with high velocity. All right. So we have this problem solved. A little later we will see what happens to the sound when you include nonlinearities. And now we will solve we will modify the problem a little bit and solve a slightly less trivial problem. Namely, let's suppose we have a gas, as we have here, and we have propagation of sound in the gas, all as before, except that now let's suppose that the gas self-gravitate, that we have not only pressure and so on, but also when we have this gas, two fluid particle or gas particle, they have gravitational attraction between themselves. It's not difficult at all to write down the equations. And of course, the interest of this problem is cosmology. It's what we are doing is precisely what people tried to describe cosmological, to describe the universe. But all right, we don't have to remember this at the moment. We just want to see how to introduce gravitational attraction here. And it's basically, we know that the force, if you have a fluid particle and another fluid particle, then the gravitational potential at the position of this particle will be simply minus the Newton constant, the density of this particle, and the total gravitational potential will be simply the integral of this over d3x1. And the force is, of course, the gradient of the potential. Multiplied by the mass of our test particle, of our test fluid particle. All in all, what I want to say is that the equation in the presence of self-gravity So here we will just put this fluid particle into the fields of all others. And the changes of the equation are minimal. I shall write them down now. So with gravity, we will still have, of course, the conservation of mass. Nothing happens to this equation. And we have still these kinematical terms. And here we have to add minus rho d alpha phi. And the phi is given by this equation. So at the first glance it looks very complicated. Well, it is very complicated in the nonlinear case. It is actually not completely solved problem. People still writing papers and papers about gravitating gas, and when they want to go beyond linear approximation. But for the linear approximation, it's all it's not more difficult than what we did already. It's just, I will explain. Although it seems difficult because you have the equation it's not pure differential equation, it's integral differential equation. But it is actually, all these difficulties are irrelevant. Let's linearize this equation. So we go again linear approximation. So we drop this term, we set it to rho 0, d alpha dot is equal to minus d alpha p minus rho 0 d alpha phi. Remember we took the divergence of this equation when we discussed sound. So we have this thing, and it is minus c square Laplacian of rho 1 minus rho 0 Laplacian of phi. And the first equation, so all in all we get the equation on the slight modification of the previous one. We get rho 1 double dot minus c square Laplacian rho 1 is equal to minus rho 0 Laplacian of phi. And now the only problem is to calculate the Laplacian. And then we can use very easily again, we will be looking for the solution in this form. And we will, as you will see, we will find a surprise. But what I'm saying is that this is extremely easy thing to do. So what is the Laplacian of phi? Remember some knowledge of electrostatics which you have. There is a similar equations and similar problems.
The density?
Yes, actually, it's just the electrostatic Poisson equation. Not a big deal, and it all follows from the relation, which again I will leave you to verify yourself. It's just the Poisson equation. So the Laplacian of phi is equal to rho, and we get 4 pi we get c squared minus or plus gn 4 pi gn rho, yes, multiplied by rho 0 multiplied by d square rho 1. And so when we go to the Fourier expansion, we find that it's the same thing, the same rho 1 as before. But omega is modified. You see, we have still harmonic oscillator, but omega k square now is c square k square. It's probably minus here. Minus 4 pi gn rho 0. Just a second. Yes, there is no Laplacian here, of course. I made a mistake. Laplacian of phi is 4 pi gn rho. And we get this formula, and with omega of k equal to square root of c square k square minus 4 pi gn rho 0. And now starts a very interesting part of the physical interpretation of this formula. First of all, you see that this is the Newton constant. And we have this expression. As you see, if k is small enough, if k is smaller than, this formula, by the way, is called the Jeans formula, the guy who first derived it. And for k, if k is shorter than the Jeans wavelength, the Jeans wavelength kj is defined by this relation. That's a critical. You see that omega is imaginary. That's quite a surprise. Try to figure out what it means. Actually, it's extremely important physically. What does it mean? We looked for the sound, and when it was an ordinary sound, we had real frequency of the sound, we have sound waves, and so on. And then suddenly we have imaginary frequency. Try to figure out what it means by looking at the formula on the blackboard. Yes?
That'd be the particles like coalesce.
The what?
The particles coalesce. Correct?
Yes, you are thinking the right direction. And but how do you see this? Look at this formula and think of what happens. This formula precisely tells you what happens. What happens with imaginary frequency?
The density either grows or decays exponentially.
Yes, right. It blows up. And now we shall figure out why. And the fact that it blows up tells you that the homogeneous distribution of density is unstable, that small perturbation will. So let's consider once again a gas. in some volume. And imagine that I will give you a hint and you will finish the logic. Suppose we have it was originally constant density inside, but then you make a tiny fluctuation. Suppose the density is slightly bigger than everywhere else. What will happen next and why?
So it'll suck up surrounding particles.
Yeah, it attracts particles stronger. When everything is homogeneous, particle experience attraction from all sides and doesn't know which side to choose. So it's equilibrium, but it is unstable equilibrium because when you have a small fluctuation, the density larger than average, it starts attracting particles. If the density is smaller than average, it starts losing particles. And so you have a snowball effect, basically. Now, however, there is another effect which actually acts oppositely. And which explains why these frequencies you see, it's imaginary for some k and real for other k's. So how would you explain this? And why? From this, the first impression from this is that for any size of this thing, you have an instability. But in fact, k is the inverse size of the fluctuation. And this formula tells you that it's only big enough fluctuations which start to collapse. So what we are talking here is gravitational collapse, but not everything collapses. If k greater than kj, which is smaller size, it doesn't collapse. What prevents the collapse? Well, we're running out of time a little bit, but actually, so when you let's turn gravity off. What was the origin of the sound wave? Why it was not yes?
Compressibility.
Yes, it was the pressure which when you try to squeeze it, you increase the pressure which acts otherwise. And so it's a interesting balance of two forces, of gravitational force which tend to collapse and the pressure force which tends to expand, tends to compensate this. And that's why if gravitational force is proportional to the size of the fluctuation. So that's why when the fluctuation is large, gravitational force wins. When it is small, frequency is real, things are oscillating. Okay, we will continue this discussion. That's actually you can learn on this. This example is quite wonderful because, first of all, you learn a lot of interesting physics here. In particular, we will discuss next time time reversal, etc. But on the other hand, it's the way galaxies are formed in real world.